Thank you. I'm Shota Yamanaka from Yahoo Japan Research. In this study, we investigate the model generality of steering law in curved path. First, I explain the background of this study. When steering through a constrained path, the movement time has a linear relationship to the amplitude divided by the path width. And this A over W is called the index of difficulty, ID. This model means that steering through a narrower or longer path has a higher ID, which requires a longer movement time. And another version of the steering law is this speed formulation, which indicates that the speed is proportional to the path width. Here, the speed means the average speed or instantaneous speed. So, in summary, the steering law indicates that the speed linearly increases as the path width W increases, and thus the movement time MT decreases. So, in our project, the long-term goal is to investigate the model generality of the steering law. For example, this ID formula A over W holds to constant width paths, including straight and circular paths. And for circular path, the movement distance A is 2 pi r, where r is the radius of this circle. And these are the simplest model formulations of the steering law. But there is a more general formulation called global model. And this is a steering law for an arbitrary path shape. So even for complicated paths, the movement time can be accurately predicted from this global steering law model. For example, even for narrowing path, the ID can be derived from this global steering law. And in addition, the movement time for a widening spiral path can be accurately predicted. So the steering law is a robust model to predict the movement time. And our research group has also studied the robustness of the steering law. These are the examples of our previous studies. So we have reported that the global steering law can predict the movement time very accurately. And in our present research, we challenge a new topic on the model generality. That is the effect of curvature. Many previous studies show that even for the same ID value, a circular path requires a longer movement time than a linear path. So this is a very natural result because you just have to carefully move the stylus in a circular path. And our question is, how about the movement time for arc-like path? Maybe the movement time is longer than linear path, but shorter than circular path. So we want to predict the movement time for different curvature values. In fact, this topic was studied before by Monteza and colleagues. They tested various curvature values, and the results showed that the average speed linearly increased as the path width increased, and the speed linearly decreased as the curvature increased. The curvature is defined as the inverse value of the radius. So this result means that steering through a sharper curve is more difficult. But a limitation of this study is that the effects of path width and curvature were independently tested. Because they found a significant interaction between path width and curvature, we assume that there are better formulations. Another study on path curvature is by Nansel and Rank. In this study, more complicated paths were randomly generated, and path width also dynamically changed. And they used the 2/3 power law, which indicates that the speed is proportional to 1/3 of the curvature radius. And this model showed a good fitness. However, this model indicates that the speed for linear path is infinite, because the curvature radius is defined as infinite in the linear path. But in actual, even for the linear path, the speed doesn't reach to infinity, of course. So this model has a limited generality for path curvature. So our research question is the appropriate formulation of the steering law that takes both path width and curvature radius into account. Currently, there are two possible formulations proposed by Montez and colleagues and Nansel and Rank. Also, based on the study by Montez and colleagues, we propose two new models that include the path width and curvature factors and their interaction factors. So we empirically compare the prediction accuracies of these models. In the user experiment, we used a direct input pen tablet, and the paths were always bent upwards. We tested 2 amplitudes, 3 width, and 8 curvature radius values. In total, we tested 48 conditions. These are the all conditions. The key point is the range of curvature radius values. The greatest radius was 28,520 pixels. In this largest curvature condition, the flight path was also drawn as a very large circle, but because we used a bitmap display, this largest circle was equivalent to a linear path on the display. So we tested a wide range of curvature parameters from circular to linear path. Okay, this is a general result of the average speed. First, the effects of path width and curvature radius are significant. As the green chart shows, the speed increased as the path width increased. And as the blue chart shows, the speed increased as the curvature radius increased. An important point is that as the curvature radius increases, the path shape becomes almost linear. Therefore, the speed doesn't increase anymore. And we also found a significant interaction between path width and curvature radius. When the radius was very small, the speed differences between 3 path widths were not so large, because users cannot accelerate in a wider path due to the sharp curve. And as the radius increased, the speed differences were more clearly exhibited. Therefore, to accurately predict the movement speed, this interaction factor must be considered. And this is a model fitness result of the average movement speed. We used adjusted R-squared and AIC values as the model fitness indicators. First, models number 1 and number 2 do not show good fitness. The adjusted R-squared values are less than 0.5. But in contrast, when we take path width and curvature into account, the average speed can be more accurately predicted. And last, adding the interaction factor improved the model fitness furthermore, because this interaction factor was significant. So this is the best model to predict the average movement speed. Next, we integrate this new speed model into the movement time model. This slide shows the procedure of the integration. The key point is replacing the W in the baseline model with V, and then replacing V with the proposed model. And then we obtain the final formulation. At the same manner, we obtain 4 models to predict the movement time. And similarly to the result of speed formulations, model number 4 is the best to predict the movement time. And this is the only model that shows the adjusted R-squared higher than 0.9. And the regression lines also show that model number 4 is the best to predict the movement time data points. Okay. One limitation in our study is that we tested limited conditions, such as always bent upwards, and we tested only constant width conditions. This is consistent with the experiment by Monteza and colleagues. So it is natural that our refined version of Monteza and colleagues' model showed the best fit. But in comparison, Nansel and Lang tested with changing path, which is a more general case of steering tasks. Also, we used only a direct input pen tablet, but the steering law can be applied to other tasks such as full body locomotion tasks, including car driving and walking. And recently, the applicability of the steering law to virtual reality environments has been also investigated. So our future work includes testing the validity of our proposed models to these tasks other than GUI operations. Okay, this is a summary of this study. Thank you for listening, and I'm happy to answer your questions. Thank you.
Yeah, thank you very much, Shota, for this talk and work. Are there any questions? Yes, please. Let's go
ahead. Hi, thank you for your presentation. My question was, if I well understood, you always use your curvature when you start like on the bottom part of the screen, then on the top, and then on the bottom.
Yeah.
So is there any change if you do that in the reverse side with the same radius?
Yeah, we didn't test that condition, but I have several evidences that steering time changed depending on the first movement of direction. Left to right for right-handed users is more faster than right to left, because this is a natural movement. And also up and down is faster than bottom to top. And also this bending direction is very natural for arm movements with pivoted by elbow. So if we test condition of bend to downwards, the movement time will be longer than other opposite direction. So the model fitness will change depending on the direction. So our model fitness will be maybe less than 0.9, maybe, yeah.
Maybe as a quick follow-up question, which is a bit more applied. So what do you expect your model to be used for? That's maybe an interesting question. For example, Fitts law you can use for designing an interface, for optimizing button sizes, whatever. So, and of course, what do you expect this? Because I have a follow-up question which underlines why I'm asking that.
So, such a task don't appear to our daily PC works or daily smartphone tasks, but our research group investigates the car navigation system to predict the arrival time. and the steering wheel can be applied to car driving. So, if this model means that driving time in a straight path and curved path were different, and so arrival time must be different for almost also for car driving. And recently, drone driving also applied to steering wheel. So this model is tested only on 2D surface, but this model will be used for other kinds of tasks in real world and virtual reality environments.
Yeah. I understand, because I was thinking about in your study, users had, of course, to stay within the path and the ways. And this is perhaps something which you do not have if a drone is flying around. I mean, you have the same, say, curvature or so, the same path, but maybe there are not the restrictions like you have, because you notice that users slow down, of course, if they approach a difficult part in drawing. And this might not apply to a drone, for example. So therefore, I'm a bit unsure about the results, whether they can directly being applied to something without these restrictions.
Sorry, your question?
Yeah, no, it was just a comment. Sorry, we can later on. Yeah. Any more questions to Shota? Yes, please. Yeah.
Sorry, just a moment.
Mm-hmm. By the way, I forgot about that. Please always state your name and affiliation. That makes it better to get to know each other, and so this would help. Just say who you are.
Thank you for your presentation. I'm Shota from Technical University of Munich. I have a question regarding what about the combination of different curves, something like a wave? Does the model also apply to following a waveform, like a sinus wave, or
like a S-shaped curve?
Or a
sinus wave,
yeah.
Sinus wave. But with multiple peaks, let's say.
Mm-hmm. Yeah. So, related to previous my comment, in fact, steering through S-shaped curve is tested by other researchers, and the baseline steering wheel fitted to steering through S-shaped curve. So I assume that this model will also fit to S-shaped curve, but this is my future work. Thank you.
All right. So if there are no urgent questions, let's thank Shota for the talk again.
Thanks
you
so
a
much.
lot. And our next